Welcome, Calculus 3 students. We are looking at vector fields today. What this means is we are going to look at vectors in 2 dimensions. Notice that I'm going to have a function in both the I and with an I component and a J component. This is representative of wind, water flow, and they also tell you stresses and strains of buildings. Anything that has a vector or a particle that moves in space and time would be some sort of vector field. Notice another kind of vector field where we have our vectors that are increasing in length along. Just look at the length of each vector because that represents its magnitude. Look at how that is variable on an outward spray from the origin. This is another type of vector field. You might even consider this being some sort of light or spray in an outward direction. Let's look at our function associated with each I and J component. Notice that if y is 0, then I have 2 times my x value for that vector, and it will just be along that x direction. Positive x's will go to the right, negative x's will go to the left. Once again, let's look at if x is 0, so we can look at the extremes of this, and you will see if y is positive, these will go up, and the negative y's, they will go down. Some combination of these, then an x and a y component will go in the outward direction, and the magnitude of each is displayed with the length of the arrow. Now, the difficult part about this, when they ask you to sketch a representative vector, for you this is going to be difficult to do by hand. We could do this with a computer program. I'm going to choose to show their graphs that they have, and we'll look and discuss those. For our A graph, let's look at the shear field that we have drawn. Notice that my x is always 0. So if my x is always 0, then these vectors are always going to be going in a y direction, and their value is going to be that of x. And as the value of x increases, the magnitude of this vector increases. Note that the positive x's are all headed up with increasing length of vector, and the negative x values are all going down with an increasing length in vector because the magnitude is getting larger. We call this a shear field. Our B graph is a channel flow, something like a river. If I have my x's all being, or my I components all being associated with 1 minus y squared, and then that J component would always be 0, note that these would always be going in a horizontal direction. I also am going to have my y values for this will always be, I will take whatever my y value is and I'll do 1 minus y squared. So my larger magnitude vectors will be that along this x-axis, and they will get smaller and smaller as I move outward, always in the positive direction. Rotation field wise, notice that for this one here, if let's say my x is 0, that means in the I direction, or my I component, will always be in an upward. So along this x-axis, they're always going to be in an upward or downward direction. And then for my if my y values are 0, my J component then would be always in that x direction. So let's look at these horizontal vectors. These horizontal vectors have a direction that is negative, whatever my y value is. These vertical vectors all have the, if it's a positive, it has a positive upward direction, and the negative has a downward direction. Then as I move along and get points that are in the middle, notice that as I move outward, the magnitude of my vectors becomes larger, all moving around this circle, originating at the origin. Next, we have a definition of radial vector fields in R2 space. Notice that R is my vector, and my vector field is capital F. This f of xy is some scalar valued function, and R is my vector, so my vector field would be this vector divided by the magnitude of my R vector. And then the magnitude of my f would be equal to this 1 over this magnitude of my r, all raised to here to the p and here to the p minus 1. So what we're going to do next is we're going to show that each point of C on my circle is orthogonal to the line tangent to C at that point. In this next example, here we have our circle of radius A, and if we look at the gradient of this circle, we see that that is the vector 2x, 2y. This gradient is parallel to our vector field, and wherever that tangent line is. Now this second picture happens to include all of those vector fields, so you can see wherever it is that I choose that tangent line to be, that gradient would then be parallel to that vector field at that point. From this you can say that our vector field is orthogonal to the line tangent to C at any point x, y. For our B, we are going to note that our gradient, and we're going to look at that gradient and the dot product of that gradient. So let's look at what that would look like. It is going to be our gradient of x, y, and then our vector field g, x, y. This is going to equal 2x, 2y, and then we are going to dot product it with minus y, x, over the magnitude of our vector. And if you do this, you will get 0. Because of this, we can say that this gradient is orthogonal to the vector field at G, which then implies that our vector field G is then parallel to the tangent line at xy. So this vector field G is parallel to the tangent line at xy. In 3 space, for our very first vector field, let us note that if we let z equal to 0, so we're just looking at the xy plane, then we have x, y, and this value is a 1. So the z component would then be a 1, which means we basically have a radial vector field. So we have this radial vector field, and then just looking at those first 2 components. Now in the horizontal planes, the radial pattern is kind of the same, but the vertical component itself, because it's e to the minus z, as we go upward, notice that the values of these the magnitudes of these vectors, if you will, decreases as we go upwards. In this next example, just notice that this is 1 minus r squared, and the magnitude of these vectors is the greatest along this center line. As we move outward, the magnitudes of these vectors get smaller and smaller along this cylinder, and it gets smaller as we get to the edges of this, and just depending on how many divisions that you choose, you know, how many different points you're looking at to draw however many arrows. This one would be longer because it's there closer to the center, and then as they move outward they get tinier and tinier, the magnitude does. We're now going to extend what we've been doing to gradient fields and potential functions, and the vector field where we take the gradient of our function is now going to be our gradient field, and phi is the potential function. In example 4, we're asked to sketch and interpret the gradient field associated with this temperature. It's kind of like a hot plate, if you will, and our function is x squared plus y squared is less than or equal to 5. So this would be our hot plate of radius 5. So our vector field f is then changing this to the gradient field is going to be the gradient of t. This would be the vector, and let's take our partials. First, the partial with respect to x would then be my minus 2x, and I'm taking the gradient here. Partial with respect to y is the minus 2y. In other words, you could say that this is negative 2 on this as a scalar multiplied by this vector xy. Now the vector field points inward towards the origin at all points except for at 0, 0. And the magnitudes of these vectors is going to be the magnitude of f is just going to be equal to the square root of, and then I'm going to get negative 2x quantity squared plus negative 2y quantity squared, and this will look like 2 times x squared plus y squared. So the magnitudes of these vectors are greatest along the edges. Now what we are showing is the gradient field f of this gradient of t. Notice how their gradient is greatest, the magnitude is greatest along the edges. And this is going to show us that the plate is hottest at the center and coolest at the edge. So the heat diffuses outward. And this value here is that gradient of our temperature vector at P. For our next example, if we would like to find our gradient field, we need this phi sub x, phi sub y. So we're going to take our partials with respect to x and our partials with respect to y. When you do this, you're going to end up with minus y over x squared plus y squared and x over x squared plus y squared. And notice that the level curves of phi are the lines y over x equals c, or y equals cx. At all points off the y-axis, the vector field is orthogonal to the level curves, which is then going to give us this rotational curve. Next, we're going to be looking at level curves of a potential function and their equipotential curves, and we're going to see how those relate to our equipotential surfaces. We need to find the gradient field associated with phi and verify that the gradient field is orthogonal to the equipotential curve at 2, 1. That's what we're doing first. Let's note that the level curves are the hyperbolas x squared minus y squared over 2, which is equal to some constant. Therefore, the slope at any point on a level curve, phi of x, y, is equal to some constant. And this would be the slope at any point on that level curve. So let's look at what the derivative at any point is. That's going to be x over y, and at the point 2, 1, the slope of this level curve is then equal to, that would be just 2 over 1, which would then be 2. So the vector tangent to the curve points in the direction 1, 2. Since our gradient field is equal to gradient of phi, and this is going to be equal to x minus y, f of 2, 1 is going to be the same as the gradient at 2, 1, which is then going to be equal to the vector 2 minus 1. And the dot product of the tangent vector 1, 2 and the gradient is equal to 0, therefore orthogonal. Alright. For the B part, we're supposed to verify that the vector field is orthogonal to the equipotential curves at all points x, y. Well, since the line tangent to the equipotential curve at xy is parallel to the vector yx, while the vector field at that point is x negative y, the vector fields are orthogonal because if you take their dot product, that will equal 0. So let's take their dot product. We said we had this vector yx, which is then the dot product of x minus y, which is our vector field or our gradient field, and this dot product is 0, therefore it is orthogonal to the equipotential curves at all points. And that concludes this section.